So now we're going to hear about classification of single lead electrocardiograms, TDA informed machine learning by Paul Samuel Ignacio.
Yeah. All right, so hello everyone, I'm Paul. I'm from the University of the Philippines, and today I'll be talking about classification of single lead electrocardiograms, TDA informed machine learning. So let me tell you about the project. This is actually one of the projects that were undertaken at the 2018 version of the MSRI undergraduate program REU. So for those of you who don't know that, it's a 6-week REU program where for the first 2 weeks the students learn about the background material, and the last 4 weeks they engage into the research. So that's one thing that I want you to keep in mind. So everything that we did in this project were done in the span of 4 weeks. So the project was undertaken by a team of 3 undergraduate students, and I was the TA assigned to that project, and so I was the lead of the project, and the project was supervised by the research director. And so because we were funded by these agencies, I would like to acknowledge them. We thank the MSRI, the NSA, the NSF, and the Sloan Foundation. So here's the team. So the 3 undergraduates, actually 2 of them, so Christopher and Luke are now seniors, and then Esteban is now a graduate student at Cal Poly Pomona. And then David Uminsky is the research director. He's also the executive director of the Data Science Institute of USF. And I also just wanted to give a shout out for them. So this project was presented at SACNES and JMM, and in both cases it won the Outstanding Poster Award in Mathematics. So what was so here's the outline of the project. So first I'll give you an introduction, and then I'll describe the pipeline, which is basically something that you've seen already today. And then I describe the point cloud generation, how we extracted the features, the classification that we use, and then the performance of the model. And so the outline, the project goal was that is to examine if TDA features can be used in the diagnosis of heart conditions, specifically atrial fibrillation. So the running joke that we had when we were doing this project is that the goal was that if somebody comes along with their ECGs with them and there's no doctor around, the mathematician will be able to tell with reasonable accuracy if they have, if they're normal or if they have atrial fibrillation or other heart conditions. So what is atrial fibrillation? Is the most common form of arrhythmia. So it affects 1% of the population. So in a normal heartbeat, the blood flow is dictated by the synergistic propagation of the signal from the sinoatrial node. And so it goes from the sinoatrial node, the signal travels to the atrium, and then a gatekeeper receives the signal and opens the gate of the ventricles, and then the ventricle pumps out the blood. And so this is the normal progression, but in atrial fibrillation, the signal in the atrium are in chaos. So for some reason, the signal in the atrium is in shambles, and then the gatekeeper, because of the chaotic behavior of the signals in the atrium, the gatekeeper sometimes opens the valve too early or too late. And this is a problem because if it closes the gate too early, and then some of the blood gets stuck in the atrium, it could clot, and when the heart dislodges it, it could cause a stroke. And so it's a problem. And so the main tool that medical professionals use to diagnose atrial fibrillation is the electrocardiogram. So an important slice of the ECG is what's called the PQRC complex, and it's basically a series of landmarks in the ECG that pertain to specific events in the cardiac cycle. So, but I just would like to focus on 2 waves: the P waves and the R waves. The P waves correspond to the electrical activity in the atrium, where there's chaos in the AF. And then the R peak, the highest peak, pertains to the electrical activity in the ventricles when it pumps out the blood. So that's why it's very high, because it pumps out the blood to the rest of the body. And then I'll point out to those features later. So our data came from a challenge that was posed 1 year before we did the project. It's basically that challenge, and this is posed by an international organization of scientists and professionals in medicine, physics, and engineering. And it's part of the Computing in Cardiology conference. So in 2017, I don't know if you read it, it says here the AF classification for single lead ECG practitioners. So every year they release a challenge, they post a challenge, and then they challenge people to give a model that does the problem, that does well in the problems. In 2017, it's the AF classification. And so they released a data set of didn't really release. There was a data set of 12,000 ECGs split into 2. There were 8,500 training set, and then the hidden test set of 3,600 was kept hidden. So And it's divided into 4, both training test sets. So into normal, AF, atrial fibrillation, other if it's not normal, but it's also not AF, and then if it's just PMAC. And so just as a testament of how difficult it is to diagnose AF, the relabeling had to be done twice. So they first released a distribution of the 4 types, and then they had to, because of some disagreements among the experts about the classification specifically, or mainly about the noisy ones, they had to redo the relabeling twice. And so this was the final distribution that was used in the challenge. Okay, so this is just the metric that was used to score the models. So it's an F1 score, which is just a metric that only takes into account the accuracy, but also the false positives and false negatives in the models. And so out of the 75 competing models all around the world, almost everyone won. So 4 of them scored 83%, so they actually declared 4 winners in this contest, rounded up to 83%, and then 4 scored 82%, 9 81, 7 scored 80%, and then the next 28 scored 70% and above. And so here are the winners. And so these are the actual test scores in the hidden test set, but they rounded everything to 83, so at 4-1. And so what I wanted to point out here is that all the models, all of those winning models, use medical knowledge. So they use features that require medical knowledge for processing or very advanced algorithms. And so what we wanted to ask is that if we didn't have that medical knowledge, if we're just mathematicians, not doctors, right? Medical doctors or professionals, is it possible to just look at the ECG and just examine the structure of the ECG alone without prior medical knowledge and be able to tell if it's normal or it has atrial fibrillation? In particular, we wanted to see if there's a signal from TDA features for telling if an ECG has AF or not. Okay. And so where does this idea stem from? So the idea is that there are 2 tail sounds in the ECGs. So there are 2 features that are being used by most of the models that are based on 2 landmark points in the ECG. So first is the R intervals. So remember I showed you the complex, and the R peaks refers to the highest point. It corresponds to the activity in the ventricles. So if it's a normal ECG, you would expect that the peaks are regular, quite regular. So if you have an AF, because sometimes the gatekeeper closes it too early, right? It affects the intervals of the peaks, the highest peaks, the RR peaks. So for people with AF, the RR intervals tend to be irregular, as you can see here. And because of the chaotic behavior in the atrium, the P waves tend to be absent. So these are 2 landmark points that are telltale signs that someone has atrial fibrillation. And so we wanted to ask, so these are very local landmark points. So we wanted to ask if the overall topology of the ECG can be used to determine whether the ECG is normal or it has atrial fibrillation. And so this is the pipeline. This is something that you've already seen. This is the same pipeline that Sarah used in the first talk. So we have an ECG. We convert it into a point cloud using sliding windows. And then once you have a point cloud, you do the persistent homology, you have a persistent diagram, and then you extract features from the diagram, and then you feed it into the machine learning algorithm. In this case, a random forest. Okay, so the idea is that if the topological features are preserved within classes of the same type, then the machine learning algorithm will be able to use that to learn and as a basis for a good classification of a previously unseen ECG. Okay, so for sliding windows, so first we have an ECG, and then so first we select a window of size length W, and then we just select, say, D points on that, on the window, and then we use it as a vector. We consider it as a vector in R to the D. So each window is sort of like a snapshot of the ECG, because the idea was to store every part of the information in the time series in the point cloud. So every snapshot of the ECG becomes a point cloud, a point in the high dimensional space. And then we slide the window over, we get another snapshot of the time series, so that corresponds to another point. So here's a movie of that. So again, as we slide along the time series, every snapshot gets a point in the point cloud. And the idea is that if there's something repetitive in the time series, it gets translated as a cyclic pattern into the point cloud. But wait. So the first question was that the first step was to choose the window size, right? So the question is, how do we choose the window size? So the problem with this strategy is that it's really dependent on the window size. If you choose a window that is smaller, then you get more features, right? So the question is, what is the proper way of selecting that in this case? And if it's too small, however, some features will be too short-lived. Remember, in the next step, we want to do persistent homology. And if the window size is too small, the circles are too narrow, I guess. So we wouldn't want that. So there's a paper by Jose Pereira that says that the cycles in the embedded cloud would be as round as possible if the period is approximate. The window size is approximately the period of the pattern. So for this project, we chose 250 after examination of the ECGs. And then we chose the embedding dimension to be R to the 50. So let me just explain this figure. So it's just a series of box plots. So we had 100 ECGs randomly chosen. And then we did embedding to R to the 5, to the 10, and so on, until R to the 100. And then for each pair, we computed the bottleneck distance, because we didn't want our persistence diagram to be too different from the previous embedding dimension, and so we did the consecutive one. So from here we see that the R to the 50, which corresponds to this spark plug, is the best choice. It's not too dispersed, and it's not too different from the next one. So we needed to strike a balance between the embedding dimension. We didn't want it to be too big, because it's very expensive computationally, but then we didn't want to choose too few points, because that would be too coarse. And so for our case, we chose embedding dimension to be 50. And then the other advantage of this approach is that it's invariant under inversion. So if you flip the ECG, you expect to find the same topological features. And this is an existing issue with the dataset that they released. And in fact, many of the ECGs were actually inverted, and very few of the models detected this. But we're saying is that in this approach, we don't even care about that inversion, because the topological features will be the same. And so so we have the point cloud. We did persistent homology, and then the features that we took were we did 0, 1, and 2 dimensional persistent homology features, and then but wait again. So what do the hosts mean? So one critic about persistent homology, sometimes the interpretation of the features is very synthetic, but in this case it has a direct meaning. In particular, the dimension 1 again represents the cyclicity of the time series. So periodicity of the time series gets translated into cyclicity of the point cloud. And so we used Ripser to complete the persistence diagram, and then from there we extracted statistical features from the persistence diagram. So we didn't know about the templates before then. So these are just the features that we use. And if you think about it, these are very naive features. We just have a persistence diagram, and then you compute statistical features from them. And this is an informed choice that we made, because we wanted to highlight that the increase in accuracy is driven by the TDA features themselves and not by the complexity of the features that we're using. And so we have a barcode, a persistent diagram, and then we compute all these features, just the mean, very naive statistical features from there. So those are all the features. And then, so for the classification, we just use a random forest. And the reason behind this is we wanted to mimic the behavior in the real world, where a disease or a diagnosis really depends on what majority of the doctors say, right? So this is exactly how a random forest works. So we hired a bunch of robot doctors, and then we asked them to classify, and then the majority wins as the classification. Okay, so this is since we wanted to see if the TDA features do help to increase the accuracy in the classification, we had two setups. First, a random forest is just 4 features, which is based on the R intervals, which is a known good feature. So just the mean standard deviation is just 4 features, and then we tucked in the rest of the TDA features, because we wanted to see, do we get something else if we tuck in more features based on the TDA. And then, so that's exactly what I said. And so, just to put it in perspective, these are the winning models in the competition, and these are the results for our model. So we didn't quite beat them, so our result is at 0.72%. The winning model was 83, but you have to keep it in perspective. They use a lot more features than we did. And another observation here is that, so we only used 23 features and we're already at 72%. And another highlight that I wanted to say here is that with just the RR features, the 4, these 4 here, all of those features were used by all of the winning models. So in fact, much of their accuracy here, is already driven by just 4 features. And with the just additional 19 features of the TDA, we don't even need medical background for that. We're able to increase it here. And just to see if, okay, so looking closer at the F scores, the atrial fibrillation, normal, and noisy, these are the results. So we wanted to see if, okay, so it does increase it, but it's actually significant. So we did a paired t-test, a one-tailed paired t-set at alpha 0.05, and we see that, in fact, all the increases that we see are significant. Okay. One thing to note here is that, so I put a footnote here, the test set has a similar distribution than the hidden one. Because the thing is, they never released the test set, so we couldn't test our model exactly the test set that they had. So what we did was, with the released training set, we extracted 1,000 ECGs. That's exactly, or 1,000 with the same distribution as the hidden test set. They didn't release the hidden test set, but they said they released the distribution. So we extracted the 1,000 ECGs with the same distribution, and then we bootstrapped the training set to recover the same amount. And then we trade on that, and then we tested on the extracted 1,000. We did it 100 times. So these are the averages here. So technically the test sets here and here are not comparable just because they didn't release that, but that's something that we could work on in the future. And that's all I wanted to say. This is the team that did this project. Thank you.
All right, do we have any questions?
Did you try to use just TDA features?
So initially the idea was to use the bottleneck distance, so not even the random forest. So we had that persistent diagram, and we wanted to see if the bottleneck distance alone is able to cluster them into the right classification. But we had too many points, so we tried to abandon that. And if we so in the random forest, I think if we don't add the 4, we did it, I think we had around about 65 accuracy without the 4 features. So yeah, so if you take out RR features here, it drops to about 65%. So what we wanted to show here is it's also the TDA features that we're talking are also compatible with the RR intervals, because it does increase it. Yeah. Yes.
So, okay. Yeah, very interesting. So when somebody has atrial fibrillation, they can still have a pretty periodic heartbeat locally, right?
Yeah.
So then I would expect the one cycle will still be kind of the same regardless of the condition, because it's mainly driven by the ventricular signal that comes through, right? So do you have an interpretation for how this is working, even when it's maybe a pretty subtle thing that doesn't globally impact?
So the thing is, the P waves are sometimes absent, but not all throughout. So there's still some break in the periodicity, I guess.
Okay. Yeah, it's interesting. So it seems like it would be a small signal. So I'm actually fascinated that it works as well as it does. It would be interesting to see if you could drill down and see like what actually were the differences that it was learning.
And sorry, go ahead.
Have you tried sub-level set filtration?
So I said 23 features, but actually in this checklist there were only 16 here. That's because 4 were the RR features, so that's 20, and then 3 were. One is the ratio of so we cleaned the data, I didn't mention that. We cleaned the data. The ratio of the clean over the original one was one of the features. And then the 2 features come from from sub-level sets. So we treated the time, so we had the same time series. We did super level sets for filtration, and then we just tagged where, so when you do super level set, it encounters the peaks first, and then some were down the road, they merge, and then we tagged those merging points, and then we computed the average, the standard deviation, I think. But in terms of doing TDA with a sub-level, we didn't do that.
So So when you are transferring into point clouds, how many point clouds you on average have for this kind?
I think we had 3,000, about 3,000.
So it is really computational.
Yes,
expensive
exactly,
To
yeah.
compute the persistence diagram.
Exactly, yeah. So initially we wanted to tuck in the bottleneck distance as well as a feature in the vector, an additional feature in the vector, but again it takes too long, so we decided to drop it.
Yeah, I mean the sublevel cell filtration to produce the persistence diagram is really quick.
Mhm.
Even with 3,000 point, I guess with Reeves filtration it can take like a couple of minutes, right?
Yeah.
But with sublevel cell you can do it within like.
Also, you're saying
seconds.
to bypass the embedding part.
Yeah.
Okay.
Yeah, you can just really produce the persistence diagram.
And then use the feature.
Yeah,
Okay.
use the
That makes sense.
Okay, I think we have time for 1 to 2 more questions.
What was the dimension you tended to embed?
The chosen one was 50, order the 50. So the ratio with the window size is like 1/5.
Because I was going to also recommend maybe alternate filtrations
Mhm.
instead of using RIPS or like an alpha filtration
Yeah.
that will have far fewer simplices
Yeah.
and will make that calculation go much faster. So you wouldn't have to
Yeah.
change the approach that radically. You would just use a different filtration.
Filtration.
instead of relying on RIPS.
That could-
Since you're in a Euclidean space, maybe alpha filtration.
Yeah, I agree with that. In fact, we had a lot of dreams for this project when we were starting it. We wanted to do, after the random forest, we wanted to do CNNs, and then we wanted to change the, instead of the diagrams, we used landscapes, but then we ran out of time. So it's everything that we did in 4 weeks.
Will this carry forward to the next year's challenge?
I think they have a different challenge.
Different challenge.
I think it's sleep apnea.
Last question?
You said P-waves are also important, right?
P-waves, yeah. Yeah, we did not include P-waves analysis at all in this one. So
Did you
that's
find a way to use that at all?
So the problem is when we do the point cloud embedding, there's no way to track which part of those are corresponding to the P wave. So yes, that's a good point. We did not at all use P waves analysis in this project.
Sorry, did I miss someone over here? Oh, okay, just making sure. All right, let's thank our speakers.